As we prepare to learn about statistical methods for estimating causal effects, we'll use this video to discuss the crucial first steps of a sound data analysis, asking clear research questions, and building causal graphs from scratch. Let's examine an issue relevant to political science and civic engagement: voter turnout. So many different parties are incredibly interested in finding interventions that will effectively get people to vote. One such strategy is the rating of what are called implementation intentions. An implementation intention is a statement that plans out when and how you'll perform a certain action. Here, voting. An example might look like, I will go to my polling station after work ends at 5 p.m. by walking half a mile to the exact address of the polling station. The idea with implementation intentions is that the writer has a very concrete idea of how and when the action fits into their day's routine. Psychologists and cognitive scientists have studied implementations in a wide variety of settings, and they can be a useful tool for developing and sustaining good habits. This lends itself to the question of interest in our investigation. What is the causal effect of using implementation intentions versus not using them on the probability of an individual voting? This seems like a perfectly clear research question, but let's dig a little deeper. These are two examples of what study participants might call implementation intentions. Would we count both of them equally as using implementation intentions? The first one explicitly specifies steps to take to get to the polling station at a specified time. The second one is much more vague. In order to have a more clear idea of what the causal effect of treatment actually means, we might wish to clarify treatment as being a clear implementation intention, one that is explicit about when and how the individual will go to the polling station. This will likely help us have more actionable results from our analysis because effects will relate to a more concrete, defined type of action. Without doing this, effects we see would be a mixture of vague and clear implementation intentions. This would make it hard to give clear recommendations. Note that we don't always have to consider binary treatments in causal inference. Perhaps there is a middle level of treatment corresponding to the second example here, using unclear implementation intentions. The methods that we'll discuss are perfectly suitable for treatments with several categories and even quantitative treatments. In this context, though, we may decide that the middle treatment isn't of interest because we likely want people to use implementation intentions the way they were meant to be used, clearly. More generally, having well-defined treatments is essential for meaningful causal inference. To give some examples in other settings, using a public service can be unclear depending on the service. What if some people use the service minimally and others much more? Undergoing a health procedure, say a diagnostic screening, can be unclear if the implementation of the procedure is different from person to person. Participating in a program can be unclear because there can be many degrees to participation. And wearing a mask to prevent the spread of infection can also be unclear. What type of mask? How often is it worn and where? Is the mask worn correctly? Returning to our running example, let's start to think about where we might obtain data for this study. Let's say that we run a political information website and that we're planning to use a survey to collect relevant information. When we start to build our causal graph, we start with our treatment and outcome node with the causal path connecting them to indicate the possibility of a causal effect. What next? We need to think about non-causal paths that may connect them. We can first think about confounding variables that are common causes of both treatment and outcome. These could include party affiliation and education level, because both could influence the tendency to vote and the tendency to use implementation intentions. There are likely many more, but for the purposes of illustrating this thinking process, we'll just stick with these two. So we've defined causal graphs as DAGs that display the common causes of any two variables on the graph. Does this mean that we also need to consider common causes of A and P, A and E, and P and E? In practice, because causal graphs are used to answer a specific research question about a certain pair of variables, the treatment and outcome, we can answer this question by asking ourselves another question. Would these new common causes open up any non-causal paths that wouldn't be blocked by existing variables? So in this example, would the new common causes open up non-causal paths that wouldn't be blocked automatically by P and E? So verify for yourself that the answer to this question is no. The addition of those common causes would increase the complexity of our graph without gain. P and E already suffice to block these paths. So these confounding non-causal paths are one type of non-causal path, but we should also consider the possibility of open non-causal paths due to collision nodes. To do that, we should think about selection bias. The S variable represents use for a website, and that variable is boxed on our DAG because it's inherently conditioned on. We're only collecting data from our website survey, so this variable is automatically yes for everyone who will eventually be in our dataset. Because S is conditioned on, it might open up a non-causal path if it's a collider on a path from A to Y, or if it's a descendant of a collider on a path from A to Y. We might find it likely that an appreciable portion of our website's users came to do so because of action-oriented personality types. This would be a very hard variable to measure or even conceive of measuring. So we'll indicate it as a U variable, U1, to indicate that it's unmeasured. This personality type also likely influences the use of implementation intentions. It probably also influences voting, but for simplicity and to focus on the concept of graph building, we'll leave that arrow out. Let's just focus on understanding how to think through representing possibilities for selection bias. So in order for selection bias to manifest, we would have to see if there is a mechanism for completing a path to Y, where S is a collision node or a descendant of one. Another potential source of users on our website might be a referral from a newsletter on social issues, which could also be unobservable for privacy reasons. We might also believe that the use of the newsletter influences voting. So as it stands, this non-causal path through S remains open. We can't condition on the personality or the newsletter variables because both are unobserved. What we can try to do is break a direct arrow into a chain by thinking about mechanisms. Our hope is that a middle node on such a chain is measurable. We might think of this mechanism. Perhaps we know that our only referring newsletter is one that routinely provides readers with printable mail-in ballots for their state. Having a mail-in ballot might be more readily measurable and thus provides a way for us to block this non-causal path. So this was a hypothetical example, but hopefully it illustrated the key parts of the thought process of asking a clear causal question and building causal graphs suited to answer that question. Once we have the treatment and outcome on the graph, we should think about the confounders of the treatment and outcome and about causes of selection that might open up non-causal paths due to selection bias. If any non-causal paths remain unblockable, we can try to block them by breaking arrows down into chains with measurable variables. So with the process of building a causal graph in our toolset, we can start discussing the next step of applied analyses, the use of statistical methods for actually estimating causal effects.